welcome to another iteration of parallel computing, offloading, OpenMP and OpenACC updates in GCC, obviously here. It's again the Bay-Libre team doing this. We have done most of the work in the area, of course, as always, benefiting from general GCC development and a number of individual other contributions. Tobias and I, Thomas, are here. Andrew Stubbs, unfortunately, can't be here this year, but he prepared some slides in particular for the AMD GPU support that he's maintaining. Right, quick introduction maybe. Tobias is, in addition to being a Fortran reviewer, he's also maintainer of OpenMP support in GCC in addition to Jakub, and maintainer of OpenACC support in addition to me. And I also maintain the NVIDIA GPU backend. And as I mentioned, Andrew maintains the AMD GPU backend. That's the agenda, I guess. Yeah, we will see how far we get. If there are things we can't cover in this session, we have the BOF coming up this afternoon, I think, where we can go a bit more into the experimental kind of things or ideas that are coming up. I first want to start with a very small example of OpenMP offloading code, just in case people are not familiar with that, or is everyone familiar with OpenMP offloading? Anyone not familiar with OpenMP offloading? Raise hands, please. There is one, that's great, then I can use a slide. Right, so here you have a function, that's C code obviously, function bar. Here you have okay, more people joining. That's great. Some local variables. OpenMP originally was meant for CPU side parallelization, but a number of years ago got extended for offloading acceleration devices with this OpenMP target construct that we see here. This means to the compiler that this region here, this structured block, should not execute on the host system where you launch the program, but should be sent to any kind of offload device. There are some clauses here. Private A means to privatize this A array in some way, not going into the details here. And then an important thing is mapping data, because unless you have a shared memory system, shared memory between host and offload devices, if you do not have that, then you have to transfer data from host to device for your computations and then back from device to host. In this case here, it's very simple because we only transfer from the device to the host the error variable in case, to verify that the program did the right thing. So then again, this section here is sent to the device for computation, and the host basically launches this GPU kernel or whatever accelerator you have and waits until it completes. Then the data is transferred back, which in this simple case here is just this one variable. And then on the host, we check whether there were any errors. So inside the region, here we have an OpenMP parallel construct, which parallelizes this for loop here in whatever way, again, not going into the details, which does some computation on this privatized A array, so that exists in GPU memory, and then does another run over the A array to look whether all the values are as expected, and does a reduction operation from the parallel runs here to basically assemble all. So this means the error variable is private for every single iteration of this for loop that runs in parallel, and at the end all the individual error instances of this variable are combined with a OR operation, and here in this case this means if one of the iterations computed the incorrect value up here, then error will be set to 1, and in the end we will have an error state or have error set to 1 here, because 1 or 1 is still 1. And then we can check that here. So that's very primitive OpenMP offloading code from this libgomp test case here, just chosen randomly. Now, of course, the interesting thing is, or two things, compiling this code for an accelerator device which is heterogeneous. So that's not typically, or what GCC supports, it's not the same architecture as the host. But it's in our cases that we work on, it's either AMD or NVIDIA GPU, which they're separate instruction sets and separate GCC backends. So that's one thing we need to do, and the other big thing is to schedule the individual iterations of these loops here onto the hardware that we have available. GPUs have multiple levels of parallelism, and we have to make good use of them to get good performance, because a GPU core itself is not a fast thing to execute general purpose code, but you get performant execution only if you schedule stuff the right way to exploit the GPU hardware appropriately. That is a non-trivial thing, and also if you attended the BOF before, a hard topic is where your data is, that you prefetch everything that you need so that it's available when the core needs any data here in this case. Yeah, that's trivial, but well, but still. Right, and so I wanted to quickly show the flow of execution in GCC for the target construct. So this, again, this structured block that needs to be compiled for GCC, for offloading, at the very, very, very high level. You have your input code here, for example, C with GCC. These are, by the way, the 3 languages that are currently supported by OpenMP and OpenACC, so that's why we list them here. When you compile with -f OpenMP or -f OpenACC for OpenACC, which is another offloading programming model extension, the compiler first does stuff as always, and additionally the regions that are marked with the target construct are split out into separate functions, and they are tagged with they are marked up so that in addition to the normal assembly code that the compiler generates, we also stream out these functions, these offloaded regions in what GCC has as the LTO format. And then we keep going down. The compiler driver runs the assembler and runs the linker. The linker has a plugin that sees that there is offloading code in the corresponding object files that get linked in. And during linking, then it calls back into the compiler by invoking a similar thing as you would do for link time optimization of your host code. But that is then the front end to the offload compiler. So we literally take the LTO front end that GCC has, but on the back of that, we do not have the normal hosts code optimization generation, but that is fed into the GPU compilation pipeline. And that, by the way, is the very same as any other GCC target, so you can also configure your GCC just for generating code for AMD, NVIDIA GPUs. Right, and then there is some other object file produced out of that, which the linker, the host linker again, then combines into the final executable together with libraries as necessary, both for host and for the offload targets, and puts that into the final binary. And at runtime, so libgomp is the support library for the OpenMP, OpenACC offloading stuff. That sees that there are some sections in the binary that contain offloading code. Then it goes see if there are any GPU devices available, and if yes, has some internal structures. And then the actual OpenMP target construct eventually turns into a library call into libgomp, which does all this initialization stuff when first called, and then sees whether the function corresponding to the structured block, whether that has a corresponding GPU variant, and the GPU is enabled and then is able to do the memory transfers as directed by the code and invoke the offload kernel. So that's very high level overview. Of course, there are a ton of details there, as you can guess, but it works. Right, that's just for setting the stage. And now Tobias takes over.
Brush over a couple of topics. If I should delve a bit more into some details or questions, please ask. Here we are. Okay, does work. In the AMD GPU, one feature which is fit more interest maybe for using. It's not too difficult to implement, but was long awaited is finally the generic ACC support. AMD GPUs on generic directly code for a specific GPU, although a class of GPUs can be relatively similar. The runtime checks that exactly for that one compile for, and we generate code. And the result was that although we don't support all of them, one has a huge number of architectures. So if one wants to write code for them, not only the compiler needs to support it, but also the runtime. So if you ship a distribution or if you want to use it, you have to configure a multilib for the specific GPU. And in mainline, we have now 25 different GPUs, and you don't want to compile at least all of them. And fortunately, NDC, we saw the problem a bit while ago, but now they finally solved the issue, and GCC kind of followed directly. Fortunately, in a way, also, I was told it trusts them that it's kind of now ready, but well, it wasn't quite, but at least permitted to have it directly in there. And they now have some generic ACC support where they group some class of systems. So now it reduces the number quite drastically. For GCC, we use the LLVM as linker and assembler. And I'm actually linker back, but for the assembler, no one wants to implement it and maintain it on the bin-util side with ever-changing ones. And I mean, that support's a bit older, but the ROCm runtime library had it in April, and GC was released in April, so it's there. And the question is, which ones one should choose? Currently, it was with can be compiled with the LLVM 15 linker right in GCC, but one and move to one, but then requires LLVM 90. The question is what one should do. The top ones is currently the one supported, and the principle instead of having 9 configs, one can have 5. The generic ones and the 2 which don't have the generic ones, but we see new runtime on the user side, a new linker and assembler. I don't know what to do there, kind of the question there. If the specific ones not available, but the generic ones, we have the for the offloading part, a nice error saying, well, use the generic one. Like an example there. That's a bit this side. The our next item that just came out more or less on a workshop paper. Co-author said they had now a testing machine of the MI300, which looks like the one at the top. Something you don't want to buy at home or quickly as a company, since the price is 5 digits. So in the workshop, kind of the way was started. Well, they have now one, so one starts naively adding the feature, which is in principle very simple. One needs to have this code for the GPU. Adds have some def file, one updates the documentation, and then in principle it works. Then you start compiling the multilib, And of course, it fails because the assembler complains that a lot of things is not supported. So you start reading in the spec, fixed items there that the assembler is happy, and try to find other things. Then you run it, and it still fails. And then you realize that you missed some point, that you have to add more not operations between, I don't know, load, which takes the multiple cycles, and if you directly afterwards use it, that was then one fix, and then some atomic fix. And one test case, then it just has some, it's extremely slow. There seems to be in some corner case with many logs not working, but otherwise it's there. And the next extension would be in principle in terms of the main AMD GPUs to get the GFX 12 series, but yeah. Anyone volunteering doing the same way? Then I have a half-working patch, otherwise I try to convince my colleague to set up Rockham on his GFX 1200 and add it. That's a bit on this one. On the other side of the news, generic one, we finally fixed some, or backup essentially did, but we have to do some configure script changes as well. An issue with the BUT view, where 2 bytes is not enough for spanning a section if it gets large, and there's a different way to do it. And well, a couple of other things. Vectorization improved, and if you improve things, then you find bugs, in this case in the math library. ULab has for AMD GCN vectorized math functions, and there was some corner case not working and some other fallout. One of the GFX 10.3 and GFX 11 system issue, and we'll post a patch on Friday, so yesterday. Obviously not reviewed because everyone who could review it is busy here. And another of the things happening there is now on the performance side, due to some work by Andrew and Vectorizer in general. The first one is really a small change. The VI mode offsets for Gamma scalar was not handled for vectorizing, and GPUs are in principle relatively slow, but can do extremely many things in parallel. So if one manages to do, in this case, vectorization, one of these spec benchmarks, it's a reference that was a third faster, and at least with some other settings as well. So like Thomas mentioned, you do kind of a host compilation and then generate device code, and in that case, another thing had to be fixed, that some optimization related to masking don't work on the host but on the device, so this feature had to be enabled, and that was a big one. And I think the other 20% was either partially due to this one, and I think partially due to some generic vectorizer work, which is great. That's on this side, and then on the video GPU side, a bit less happening. It's a bit easier in some cases because the PTX assembler is then directly compiled for the specific GPU. So except if you want to use new features, you don't have to keep track of all the GPUs. But a couple of things happened. One important change in the GCC 15, I'm not sure exactly whether it was mentioned last year at this time or a bit later, I think it was already, was getting some issues with offloading to, well, systems which are slightly different in vectorizer. The AArch64 RISC-V is also affected. It was done by Prathamesh from NVIDIA last year. Global constructors and destructors work, which are important for C and C++, and also for the Fortran runtime library for I/O. So something happened there, and there are a couple of other smaller things, especially the LOCA.
I can quickly add to that. So global constructors in the C++ sense, for example, they are not directly relevant for the use case of code offloading to the GPU. Well, yeah, they also are in some way, but the main motivation when I implemented that was actually that I could just run the C++ test suite of GCC, because that obviously would like global constructors to work. Otherwise, you get a ton of fails all the time, which we still get enough of. But when diffing between before and after when doing development work, that greatly improves the test results. So that was my main motivation, just for basically testing the NVPTX code generation. Yeah, and similar for this alloc-A support. So PTX is kind of a high-level assembly language that is used for NVIDIA GPUs. alloc-A is not supported in the baseline version that GCC compiles for. Some newer versions support it. And we can enable that with march whatever and mptx whatever version appropriate. But then there is code in lib standard C++ or lib support C++, which wants to do unwinding. That is compiled in, and other code that just uses variable length arrays in whatever places which might get called. And currently what happened is that the NVPTX offloading compiler said, well, I can't support alloc-A. Okay, I give up. That's not useful if you want to compile lib standard C++. And then, of course, I could have added special cases for all that code and just removed those pieces for NVPTX, but that seemed more effort than adding this flag here, fake PTX alloc-A. And when that flag is passed, the compiler, instead of erroring out, just inserts a function call to a fake alloc-A function, which then at runtime aborts, because most of the cases I have seen is that the code that uses alloc-A is not relevant for our use case of code offloading. So we still don't support alloc-A in these configurations, but we still compile the code, and as long as at runtime you don't run into that code, you're fine. Yeah, that's just one of the fun things when you work on constrained architectures in GCC. You have to find your way around to make them work in the general framework. Yep.
Yeah, and GCC 16 has some minor changes, but I think you removed the slide because they are not so relevant. Well, let's move to OpenACC. There's on one hand a bit work and progress in GCC 15, where we had OpenACC 2.7 a bit extended like previous one. There's still some outstanding review work on array struct reduction and bumping the version number. We have also some other, especially in some vendor branch, publicly available, some patches which we badly need to upstream, especially on the OpenACC side. For GCC 16, a bit motivated by a couple of real-world application, a couple of things were added. AC-mem copy device was, for some reasons, long outstanding. Then a couple of OpenACC 3.x features. And the 3.3 feature is kind of interesting because there one attaches, one has on the host a pointer and which points somewhere to a pointee, and you want to do essentially the same on the device if it's available, but so you need to have the device version of the pointer address, device version of the pointee address to attach it. And the problem is, in most ways you write it in Fortran. There are cases where you create a temporary, and of course if you have a temporary, then you have the pointer address of the temporary, and that doesn't work well, so that needed some special support in the front end. So really kind of a built-in and not really a library call. And the next item is also a bit interesting because some real-world code was insisting on using clauses where you say put this named constant on the device, and GCC was saying, sorry, that's not a variable. And then after some discussion in the committee, it was decided, yeah, the standard it changed, that it's permitted because it's used in real world code, and the implementation is permitted to optimize it away or essentially ignore it, what GCC does.
That's maybe also a good comment to make. So both Tobias and I are also active in the OpenACC and OpenMP standard committees, and can use that to resolve any issues during implementation when we figure out, well, what does that actually mean? How should we implement that to be compatible with other compilers?
And the last one was actually a bit motivated. When I quickly looked at the results on the next page, I realized that for some reasons when implementing that, it simply, the Fortran part was missed. Putting the header in, I mean, that's not really much work, but it was missed. Yeah, coming to what I just mentioned, there exists a nice test suite. So NITE at the beginning of this month or middle of this month sent some results around several people about the coverage of OpenACC with some test cases. So that's their slide on what they test for. Especially on Fortran side, they don't test as much as they like to, but otherwise they seem to be pretty happy. Of course, like all test suite, there are also a bit bugs in the test suite and corner cases, so that needs to be fixed. But in any case, that's the result they got for running it with a couple of compilers, essentially the NVIDIA compiler, the Cray compiler, but only for Fortran, and GCC and GC15. It's Thomas did some final C++ fixes after 15.1 was released, so the numbers are, especially C++ side, a bit better. So one sees none of the compilers really gets everything right, especially the runtime. Partially compiler problems, partially test suite problems, and yeah, I think especially on the compile side, it's somewhat decent, also compared with the Cray compiler, but there's obviously room for improvements. I also had one pull request to them for fixing some test suite issues. Some are known, they are currently going through the pull request also from others. And the small regression seems to be because something went wrong in their testing what failed.
Yeah, as in every test suite, there are some flaky test cases that sometimes pass for unknown reasons because they shouldn't actually, because GCC doesn't implement that feature, but yeah, you can't resolve everything. There's not enough.
And in the bug report to that feature, actually, it said that it still needs to be defined at a standard what exactly it should do. And I looked at the issue. It's a bit older, but still hasn't been done. But yeah, that's the other problem, that you find issues in the standard and it takes a while. That's a bit on this side. Let's move to OpenMP quickly. I think just because it's a nice feature, GC is kind of ahead of it, and I want to go a bit more in detail to about interop. That solves a bit of problem that on one hand you have very optimized vendor libraries which do a lot of math things, which you call directly, and on the other hand you have some preparational codes and some own code you want to run on device. So you use one on OpenMP, for instance, or OpenACC would work as well, and the other one, and then you have to relate at least the device number, which is not obvious, or you might have for running things asynchronously, you want to get kind of a streaming object to work with the vendor libraries, but you still want to have the dependencies. So that's now in GCC15 mostly implemented. There's few minor corner cases not implemented, but they're in the 6.0 version. That's the Fortran support. It's in 6.0 and supported. Actually, it was deferred to 7 when I looked into it, and it said, it should be easy to add the Fortran one. So kind of one day after it was moved to OpenMP 7 in the schedule, it was then went in scheduled for voting, or at least discussion. That's in there, and a couple of other extensions I want to show. And for using them, you have different front runtimes. Of course, the CUDA one on the NVIDIA side, and HIP, which is kind of the CUDA version. On AMD, which mostly function-wise, it's just a renaming of CUDA to HIP in the prefixes is supported, and therefore HIP also works on NVIDIA because it's just essentially defined to the NVIDIA version. HSA is the internal one, which was also added. Someone requested it, and just to show how that works, the first part's a bit, as Thomas explained a bit, one does something on the device asynchronously, one does something on the host asynchronously, then one creates the interop object and says, I'd like to have a CUDA object, and please create a stream. And then the dependency, the asynchronous one gets some object back, and then one has some routines to say, please tell me or confirm that I got the version I want to have, the CUDA one, otherwise I have a fallback, and then one can get the streaming object out. That's one of these features, which in principle is quite nice and avoids also some performance issues because the libraries are highly optimized. Just to show some semi-automatic use, it has to be in a dispatch, so it's kind of controlled where it gets called, but otherwise the clavariant says, if I counter this function and under certain conditions I call a variant function, and in this specific version, so that's the one DAXP, the second one, but lower middle, and the top one is the in this case HIP version of it. It takes an interop object and it works directly by calling the device version. So this declare variant in the middle says, please append and create and append the streaming object, and please convert the pointer arguments to the device version. And that's one use of it, just to show what can be done there. The third one I just want to flash, you can also do the same thing with Fortran. And internally, we just open the runtime library. The HIP one only when used for this one, the other ones are anyway used internally. And there's some data thing, and we are happy that at least for the HIP one, we don't need headers and so on complicated because it's rather simple. Otherwise, we had to deal with a couple of complicated headers. Anyone? In general news, I don't go through this list. GCC 15 added a bunch of OpenMP stuff. The 16 one is a little bit more bug fixing so far and partially upstream, partially also, except that adds a few things here and there, a bit 6.0, a bit backlog, and to the backlog a bit on the next slide. So the current goal is to complete the 5.0 or 5.x. For 5.2 is the latest of this series, which is only smaller additions. 5.0 was the big one and took many years to get mostly implemented. The same issue have all other compilers as well. And I think we finally, as all compilers, and especially GCC, reached there. 6 has been also released last year, so more work to come. And the goal is now to get the full one. And so the items is mostly, 5.1 is mostly implemented. We need to finish some upstreaming work as listed there. Some is also reviewed, some things. And then for full things, we need to fix a couple of bugs and some minor features listed there, especially virtual functions in 5.2, iterator, version bump. And there are also some quality of implementation things, like, well, the first one is question with 6.0 or another one because it was added as clarification in 6.0, but it sounds a bit more like a new feature, although Clang supports it. And then unified chat memory and various fixes. That's a bit on the to-do list. That kind of gives mostly the status. It's a bit misleading because the level of detail on the left is for the 5.0 is much coarser than on the right. And for 5.2, it has also many lines which are in red, which are deprecate. And since we don't do the version bump yet, it's deprecated. But otherwise, it looks as we have most of 5.0 and 5.1 implemented, except of the tooling support, which is for tracing and the special debugging support. For 6.0, there's a long list of things to do, although a couple of things have been done already. And as said, upstreaming, fixing a couple of known issues, and version things will be on the to-do list in the short time on our side, and I guess most important also from the user side. And the other one is, of course, the topic performance. That's a bit work in progress. We could see some progress already. So in general, one can say on the host it's decent, although several have found some issues there as well. Offloading has a huge problem with being latency issues, copying the data there and getting it well organized with the parallelization and so on is hard. So in general, all compilers have a bit problems. I think with OpenACC and NVIDIA does a relatively decent job, but external library said, no, we don't want to do OpenACC, OpenMP for offloading. We move directly to low level, so directly CUDA HIP kernels where there's less overhead and less support, but that's Cocos does. But still, having said all the issues there, GCC could do better and partially much better. And the problem is if you get vectorization wrong, one fix, it was 30% quicker, and there are a lot of those cases, and following ML laws is you fix one issue, then the next one becomes the bottleneck, so you need to fix 10 of them or so, and there are easy cases where one should be 30 times faster to have some decent one, and that's a bit the next topic, and you quickly.
That's maybe one comment to be made. So Belibre and before where we are doing service contracts for external customers, and so far their focus has been on implementing OpenMP, OpenACC features rather than looking at the performance aspect too much. I guess somehow people were hoping that would just come by itself automatically. It didn't quite so, but that will be our focus going forward, in addition to completing the features.
I mean, it was not completely ignored. I mean, some vectorization work was done, and if you try to implement a new feature, you try it, but there are a lot of things. And unfortunately, there's also quite some overhead, and one needs to think about some of the lines ones. So launch overhead is a huge problem in some programs which have really tiny kernels. They run very often. Other programs have kind of main program loading the data, huge offloading code, ending it, writing out the data. So that's kind of the two use cases in real world. So we need to make sure that every data gets to the GPU, especially on the AMD GPUs. We vectorize the innermost one, so it's kind of 3-level parallelization. In the OpenMP sense, teams, threads, and vector. And some other compilers get rid of the vector part and try to do it a bit in the SIMT-like way, getting it a bit on threads one, which helps if you cannot vectorize. That might be an idea there to at least optionally support this. Similarly, some other compilers I thought at some point at least, I'm not sure where they stopped that, also were thinking of going from the 2 levels to the 3 levels optionally. I think the LLVM was at least some effort. I'm not sure whether they stopped it or have implemented or not. And then we have, of course, IPA inlining, LTO on the device itself and things like that. So parts are planned, and OpenMPT, so this the tooling interface where you can enter with a tool and say, now you reach the parallel region and so on, helps with debugging the code in terms of performance where it gets stored, us and of course also users, and that's probably coming also relatively soonish. And of course one needs some help with the others and gets some help also independently. And yeah, therefore some ongoing tasks. The top ones are completely separate from us. So Josef, who gives a talk tomorrow, who's a student of Honza, looked a bit into the IPA one, because a lot of the patterns is you have some code section, which can be a region before, which you put in a separate function, which you either handle for the parallel region on the host or putting an offload device and so on. And then it gets the function pointer and the arguments, so what you get passed there, and well, and then the interprocedure analysis says, oh, punks pointers appeared and whatever I cannot do, but usually it's a static function and you know what gets in, how it's read, so you can do some optimization, but don't ask me for the details, ask Tim tomorrow or in between looking at that one. And the patch, if I understood Hansard correctly, is nearly ready to be submitted. He half finished writing the code review. Another one that's a bit more related to the host code, if you get hugely parallel, Matthew saw some issues where things could be faster if one has really a huge number of parallel threads, and he started looking at some issues where one avoids having barriers at the top and the bottom and trying to get it with one. So there are 2 patches which I hope that Jakob can look into it because he knows this part a bit better than me, and there's some work going there. And on our side, it's a bit on the other side. As mentioned, device side LTO is there, then these going from 3 levels to 2 levels, and a lot of the other items which are a bit work in progress, and like the vector bug fix, which went faster. Just kind of mentioning benchmarks, not really showing so much data. The CPU one, which in general is quite good and heavily looked at SUSE side. Probably we should look a bit more on the code gen side, on the offload one, as one can use it embedded wise. The main ones are, of course, spec HPC and Excel, which test OpenMP and OpenACC. The HPC one uses MPI, so if one goes to the huge data set, one can kind of fill the whole supercomputer. So at least the large data set is not you do in a single system. You have some other benchmarks like streaming ones, and probably can add some more. So essentially that compiles and works, and at least with the current system there are a huge variation of the runtime, so going to something bigger might be difficult. So the swim benchmark at the bottom takes 0.2 seconds in the smallest data set, so that's a test mode. There's trained for PGO and ref, and then we have some which take 4 minutes, but essentially it works there. Some meta-directive issue where we do optimize later than checking for things like collapsing a loop, which then inside has a SIMD, doesn't work unless it can be optimized away. And the OpenACC ones were, because it's a bit better defined for the ACC parallel and not for kernels. Where it does more on spec HPC also runs. Since we got the code recently, we found a bug in the cloverleaf on OpenMP. There's a Fortran deep mapping bug I need to fix, and OpenACC bug that's a problem where the code doesn't follow with is present, whether the pointer or the pointee is present, and that's a nice issue because the specification says it should be as GCC has implemented it, but there's a comment in the specification as well which says that until all the code has changed, a compiler should behave as in OpenACC 1.0 instead of 2.0, so that needs to be fixed at some point as well, but that's kind of the issue we run into why it fails with data's not mapped in the LBM test case there. So that's a bit of work on the spec side and still to see, and for the others one has to check. Getting some real data, so that's OpenMP only. That's now the ref, still the tiny mode, but on a ref data set, and run with 8 MPI ranks and 1 GPU, or kind of 1 GPU hardware-wise, it's 4. Sockets also a system, but on Frontier, and compared with June to September, the graph on the right-hand side you saw before, the other one are the full ones. So one sees there was progress made, especially this Gabba load, and I think some other code optimization by the vectorizers, Hammer or Richie or someone else fixed the other one. So there's progress here. And now I give Thomas the slides and he can continue with the last ones.
Right. How much time do we have left?
22 minutes. If we go full, but then I think you leave a bit time for questions and a bit time for changing computers.
But end of session is at past, I think.
Yeah, but
Okay.
questions, and Honza probably wants to put his laptop up too.
Yeah, sure. So we don't have much time left.
Yeah, go ahead.
Okay, we have some more slides, but we can also defer those to the BOF. But yeah, I quickly go through this one. So we set up or proposed Google Summer of Code projects every year, where Tobias and I are mainly the mentors for this area of work in GCC. We had one this year. That's an idea I randomly had last year and put up on the list and got a student working on it. Actually, 2 were interested. We could only pick one, obviously. And you may wonder what's the use case for that. Implementation of a simple in-memory file system running on here a NVIDIA GPU. Yeah, right, as written here, that was to implement a volatile in-memory simple file system running offloaded on the GPU, so non-persistent, but just when you launch some kernel, you can write a virtual file and read it back, stuff like that. Which on one hand seemed a nice introduction for a new contributor to have a small piece of work to do and doesn't need to care about all the compiler level lowering of offloading constructs and all that. And on the other hand, it has an actual use, as I will mention shortly. We use newlib as the C library for the GPU offload targets. Newlib typically interfaces with using system calls with whatever kernel there is. On a GPU, we don't have a kernel. It's basically a bare metal system in that regard. So we have to implement something. One idea was that this might pave the way to have an actual RPC-based interface to the host, so that on the GPU you can read files from the host. We're leaving that for later, just doing the simple thing first. And of course, now what is the most exciting thing to do in a presentation? Of course, a live demo. So I shall be doing that quickly. Connecting to a laptop at home, because this one doesn't have an NVIDIA GPU. So this is a GCC build for AMD and GPU offloading support that I have, including the newlib C library. This is a simple code here, a main function with an ACC serial construct. Serial means this is just running with one thread on the GPU, OpenACC, so the Pragma ACC is OpenACC support. Could likewise have used Pragma on target, I guess. In there, I have some stuff here. ACC on device functions, I can use that to have diverging code paths, whether I am executing on the host or on the device. So you can tell from the message here what's going on. And then in this offloaded region, I can use the C library fopen to open a file, check that, use fprintf to write into it, close it, and then open the file again in read mode. And fread from that, always doing error checking that I get the expected things, and then use printf. Also printf inside the offloaded region. For NVIDIA GPUs, there's an intrinsic that we can use at the PTX level, which does some interfacing with the NVIDIA driver to actually print your stuff on the host console, or whatever standard out points to. For AMD GPUs, we have actually implemented an RPC system, so the host, while waiting for the device to complete this section of code here, actually polls the device if there's any data or other actions to do, or any data for printing to the console. On the right here, there's just some random code snippets from the implementation of this virtual file system. And then I compile this. That's just a command line. It's so huge because I use the compiler and link to the libraries from the build directory. So if you just compile and install GCC, you don't need all that, but just run GCC. Normally, the important thing is I'm using here this, specifying this file that you have just seen and enabling OpenACC and some, yeah, that doesn't matter here. So compile that. We can gloss over the messages here. So if I now run that, interesting thing, actually libgomp is not able to load the GCN and NVPTX plugins, but has a fallback mode. So this OpenACC, wrong window, this OpenACC offloading region then actually executes on the host instead of on the device. And then we get the message hello from host, because that's what this ACC on device function did. And so on the host, that's not surprising. We just call into glibc, so that should work as expected. Now, the reason that libgomp can't load the plugins is because of some run path, R path, dynamic linker changes. I never really got behind that, but I can use patch ELF to add the R path to the host directory here where the CUDA driver actually is. Add that to the executable, or force R path instead of run path. Talk to the linker people if you want to know more, and run that again. And then we get hello from device. This code has now executed on the device.
And we have 5 minutes till the end of the session.
Yeah. All right. That was just a quick demo. I could show you that it's actually on the device, but yeah, you believe that, I hope.
Okay.
And the C++ support, maybe we leave that for the BOF and now
Well, you can
do some questions.
quickly say that essentially we now build live standard C++ on the device, and a lot of things now
We can
work.
do stuff like that, have an OpenMP target region and instantiate arrays in there and use standard ranges equal whatever reverse views, whatever fancy C++ features you might want to use. And
Yeah, I mean, that was the main part. Initially, it was kind of the stripped down version, but then we realized that the stripped down version does not have allocators in there. So essentially, everything is supported in terms of compiling, but of course, file I/O so does not work yet. Like the other one, but in principle,
Freestanding and libstdc++ is probably too.
yeah, as I said, the freestanding misses allocation as main thing, and I think most of the code, the initial one was that the new was missing, and that did not help. I think there's not too much to add this one, and then I don't know, can we jump to the last slide, or do you want to quick talk about anything there quickly?
Let's do some Q&A before it's over.
Yeah, but therefore I was suggesting to jump to the last slide, which shows quickly the other one, says thank you, and we have the question. So related IPA LTO profile feedback is here. In the afternoon, we have the BOF, which was mentioned also here, and both tomorrow bit related is vectorizer, and the mentioned talk by Josef about this interprocedural optimization over device ones. But no questions to this one, or remarks, comments.
How does ConspExpr work with mapping?
You ask me, I don't know. I'm not a C++ guy, really.
How is it supposed to work? Should I answer? From my reading of the spec, it should work. That's the one thing I noticed on the mapping area that wasn't there. But it currently does not, and I would like for it to work in the future. So that you do not have to map ConspExpr variables. So it will just do this thing. Of course, if you ODR use it, then it's a little bit different. Then you probably have to map it. but it's something that needs to be discussed with OpenMP still.
But in my understanding, that would be a quality of implementation issue, really, because
And specification issue as well. Yeah.
quality of specification. Yeah.
Well, most of the APIs, most of the APIs are not declared const express, so you can't use them. So you can't ask inside of const eval function whether you are on the host or a device. That would be just weird.
It's definitely not usually relevant, but there are cases where you might have some sort of, I don't know, mathematical constant that you're using in a target region where you wouldn't want to have to map that. And right now, as it is, you do have to, unfortunately. So like pi, for example, right? And you just want to use that as is in some sort of calculation on the GPU. Right now, what we've known, it maps it by default, unfortunately, instead of like just replacing it as a constant, as you would expect it to.
To some extent, the IPA propagation into the kernels could help with that. But
That is right.
I don't know why I moved over here because I have no response to that one. I don't know at this point. But maybe that would fix it.
Yeah, and that's of course also const expression for C now, and the semantic is also slightly different. Probably replacing it directly would work, but it's a bit more, I think, on the C side. But I'm not completely in the depth of C23, where the idea is a bit more that you really create something variable and then have it, but
it's the simple cases that I would want to work anyway. So
yeah.
The C23 version is what we should make sure works, in my opinion.
And I think we should close the session now and give Honza the chance that he doesn't lose too much from his BOF, and some topics overlap anyway.
Yeah, thank you for your attention.
Yeah.
And reach out to us for
Okay.